the South American Geometry Seminar. Today we're having Leonardo Cavenaghi. He presents some joint work with Llohann Sperança from Unifesp here nearby. Leonardo is a ecumenical character. He did his undergrad in Unicamp, then he moved on to USP for his PhD. Now he's in Fribourg, yeah?
Yeah.
And I should also mention that we were very proud to see Leonardo's thesis be awarded the prize for the best thesis in the country for the past year. So well done. That was great for geometry in the country. It's sure was very well deserved. And so today Leonardo is going to tell us about non-abelian symmetries and scalar curvature. Please go ahead.
Okay, so I will just put my slides here. I think that everyone can see in full mode, right? Like presentation mode, I believe. If you can give me some audio confirmation, because at this very moment, yeah, okay. So okay, so to begin with, I would like to thank you very much, the organizers, for the opportunity. It's such a pleasure to speak to you, and especially because I have a straight relation to the organizers. And Henrique was my former advisor when I was an undergrad, and also, but also underground, I guess. And yeah, so let's talk today about non-abelian symmetries and scalar curvature. This is a very, very recent work that was made in collaboration with my former PhD advisor, Professor Llohann Sperança. And it's natural that this work has been done with him, because as you shall see during my presentation, in the process that I'm telling the story of this result and how we obtained it, you're going to see that this is natural from the development that we obtained on my PhD thesis. So perhaps the main reason why my thesis was awarded is that because it established a natural scenario to future problems. That's what I want to make it clear today, and how non-abelian symmetries comes naturally in this game. Okay, so to begin with, I always enjoy to talk a little bit about the difference between topology and curvature, since this has been focus of huge research in differential geometry and geometric analysis. But today I'm trying not to be that philosophical as I'm used to, but to go straight to the point that we are going to discuss the space of metrics with positive scalar curvature on compact manifolds. Okay. And then I would like to say that in the frame of compact manifolds that happens to be also simply connected, a lot of studies has been done, in particular the ones emphasized by Nishinovitz and Hitting, and their results of Gromov, Lawson, Stoltz, and more recently this one of Ebert Ivermeller. Okay, but to recall a little bit of history and just to motivate our path, I would like to point out that from the works of Kasdan-Warner, the famous problem of studying which are the admissible functions as scalar curvature functions to manifolds that are closed. And this was very studied in the 60s and the 70s, but it regained a huge interest recently. And but the point is that at that time when this problem was posed and also solved on very, very general case, to not say that in all cases, the company of the classical Yamaha problem that happened to be solved meanwhile allowed people to put compact manifolds in 3 classes that you are gonna represent here by these 3 letters, where this calligraph P here stands for parabolic, and this calligraph E here stands for elliptic, and this N here stands for negative. Yeah, so quite different, okay? But let's see what this is about. The class of parabolic manifolds is the class which every function is the scalar curvature for a metric on such a manifold. Here we always considering the dimension greater or equal than 3. Okay, so the positive class or the parabolic class we are going to name as the class of manifolds that are closed but with dimension greater or equal to 3. such that every function can be prescribed as the scalar curvature of some metric on such a manifold. Moreover, to the elliptic class, we have that the class of smooth manifolds such that a function is the scalar curvature for some metric on such a manifold if only if its function is zero or negative somewhere. So a little bit more restrictive. And the class of negative is that of such manifolds which a function can be realized as a scalar curvature of a metric on this manifold if and only if it's negative somewhere. However, on 2019, when on 2000, yes, I think it was earlier, 2017, when Professor Llohann and I were discussing some theorem that I'm going to present here, it came out the question that, well, if we have manifold, a closed manifold with an Riemannian manifold, so we have a background metric there, and we assume that there exists an effective action by a group of isometries that we shall, let's may assume that this is also compact, then is it true that given an invariant function, smooth invariant function on this manifold, the class of such manifold can be prescribed, such function can be prescribed as the scalar curvature for some G invariant metric. So it's more or less like the Kasdan-Warner problem about asking the admissibility of smooth functions as the scalar curvature for some metrics. But here we are also asking that if you added the hypothesis that the function we want to prescribe is invariant by the group action, meaning that it is constant along with the orbits of the group action on the manifold, is it true that this function can be realized as the scalar curvature of a G-invariant metric? And it happened that this was not known until this year, where Professor Llohann, myself, and Professor João Marcos Doal from Federal University of Paraíba obtained the same classification due to Kasdan-Warner in this scenario. And what was curious about this classification is that the group of isometries, it has non-abelian in the algebra, then the manifold that admits such an effective action by this group of isometries necessarily belongs to the class of positive, to the P class, to the parabolic class, but with this index of G, meaning that every function, every G invariant function is the scalar curvature of a G invariant metric on the manifold. But where do this non-abelian thing play some role here? Just before continuing to do this, I would like to say that, well, if we have that under this condition of the presence of non-abelian symmetry, implying that our manifold belongs to the parabolic class, what can we say about the structure of this parabolic class, or of this space of matrix, of the space of functions, okay? And now, not the space of function, but this, what can you say about the admissible geometries from manifolds belonging to this class of a positive, this parabolic class, meaning that every function can be prescribed as the scalar curvature? Well, here on this theorem of Ebert and Wehmeller of 2020, I'm assuming that the manifold is also simply connected. And they obtained a very, very strong result in terms of classification that says the following. If your manifold that has this dimension that is greater or equal than 5, but not 8, and it has the property of admitting any scalar curvature, any function as the scalar curvature for some Riemannian metric, then if your manifold happens to admit an spin structure, then this space, okay, of a matrix of positive, this is space of that we say that the homotopy type of this manifold in terms of matrix of positive scalar curvature is homotopically equivalent to the space of matrix of positive scalar curvature on SN. So perhaps from now on, I shall make a little change on the notation. We had defined this parabolic class there, but now to this theorem of Ebert and Wehmeller, when I denote by PM, I say the space of matrix with positive scalar curvature, okay? So we had this thing that we had this parabolic class, meaning that every function is the scalar curvature of a metric in M. But I should mention here that come from the results from Kasdan and Warner that if a manifold admits a metric with positive scalar curvature, or at least non-negative scalar curvature, but that is not scalar flat, meaning that it has positive sign on one point, then necessarily such a manifold admit any function as a scalar curvature of some metric. So it's natural to us to denote from now on by Pm the space of metrics of positive scalar curvature on a fixed manifold. And then this result of Ebert and Vermeer says that if the manifold happens to admit a spin structure, then the space of matrices with positive scalar curvature on this manifold is homotopically equivalent to the space of matrices of positive scalar curvature on the sphere. But if Mn is not spin, does not admit any spin structure, then necessarily this space of matrices of positive scalar curvature is homotopically equivalent to the following space of positive scalar curvature. What does this denote? It denotes the following. You take the only non-trivial vector bundle that is -1 dimensional over S2, and then you consider the sphere bundle associated to this bundle. So this bundle here admits a metric of positive scalar curvature, so this space here is not empty, and then it happens that if M is not spin, then these are homotopy equivalent. The point is that to prove such a result, they use some very hard generalizations of some classical surgery and cobordism theory. And to our presentation today, we focus on very analytical tools, like PDE tools indeed. And this is only possible because of the presence of symmetries, assuming the G invariant scenario. More precisely, we have this theorem here. If a manifold belongs to the parabolic class that is G invariant, meaning that it admits any function as the scalar curvature for some G invariant metric, every G invariant function as the scalar curvature for some G invariant metric, and happens that G is non-abelian, or even better, we just need that the Lie algebra is non-abelian, then necessarily the space of metrics of positive scalar curvature that are invariant by this group action on this manifold, it is homotopically equivalent to a point, meaning that this space is contractible indeed. Okay, and I want to tell you the story about how this insight come to prove this result, because if you just take a look here to this theorem by Ebert and Vermeer, you see that is not that natural to suspect that this would happen about this space of positive scalar curvature matrix would be contractible. So how at first do we obtain some insight about the plausibility of this result? And it all starts in 2015 with this theorem of Searle and Wilhelm, that we have a manifold with an isometric action, and that is also effective on a closed Riemannian manifold, and we assume that a principal orbit of this action, it has finite fundamental group. Moreover, recall that on the regular part, we have a Riemannian submersion from this regular part to its orbit space. And then we can put a Riemannian submersion metric, and we assume that the quotient, the Riemannian metric on the quotient, it has positive scale, a positive Ricci curvature. Then necessarily we can lift positive Ricci curvature from the orbit space to the whole manifold. Okay, so we have this technical hypothesis about a principal orbit having finite fundamental group, meaning that, well, we can exclude like orbits that are like circles and stuff like this. And then we ask about how can one lift the positive Ricci curvature, and it suffices that the quotient for when we are in the setting of on the G invariant setting, then it suffices that for lifting positive Ricci curvature from the quotient, that such a principal orbit it has finite fundamental group. Then the authors, they prove that M indeed admits a G invariant metric of positive Ricci curvature. But why I'm talking about positive Ricci curvature when the talk is concerned is scalar curvature? How certain things are related? Well, these are related in the following. The proof of Searle and Wilhelm result, it has a deep step that is based on Cheeger deformations. Okay, and what is a Cheeger deformation? Here I put this cross diagram here just to make things better illustrated. But we have it the following. Suppose we have a manifold MG here, with a metric G, and we have an action of the group G on this manifold. And then the idea is the following. We want to introduce a one-parameter family of Riemannian metrics on M, such that the initial metric is the original one, G. How can we do this? Well, we make M times G, okay? And then if we just put here this bullet action by simply acting on the second factor, here P times P are a point on M times G, and then we introduce this G action here by just multiplying the second factor, then the natural projection onto the first column just result this thing here. We obtain the same manifold. But if we make some twist on the action by this expression, so this is what we call the star action, then we also obtain M as the quotient. And if you take a close look, you're going to see that this action is nothing more than the action that obtain this M here as the total space of an associated bundle to this trivial bundle here. Okay, so it naturally gives you the manifold M. But the point is that we can introduce, we can consider the product metric here, but when we consider the factor given by the group, we introduce this positive parameter t here. So this projection, the corresponding projection on this action, when you obtain the fiber bundle construction to M, then it induces a family of Riemannian metrics on M that are parameterized by t. So it all fits on a diagram like this. That doesn't really matter to our contest today, but it has a lot of different applications when we take a look like this. But then the point is that you can ask, but why we should care about Cheeger deformations, how a Cheeger deformation would look like? And the point is that if you have the complex plane here, and then you consider the standard circle action on the complex plane, then a Cheeger deformation of the classical metric that is induced by the natural metric on R2, but when we see this R2 like the complex plane, then a Cheeger deformation, it shrinks the manifold in the directions of the orbits. Okay, so we obtain something like this. And in particular, if you see here, we are in a thing that is plane, but here we look like a paraboloid that happens to have a positive Gaussian curvature. Okay, and this is very interesting because Cheeger deformations, they enjoy the property of maintaining the horizontal distribution given by the complement of the orbits of the manifold during the G action, but also it enjoys the property of being non-decreasing in terms of sectional curvature. So if you denote here by kappa t some appropriate reparameterizations of the sectional curvature of the metric gt, then we obtain this expression here. That doesn't really matter, in fact, what terms are here, but just note that zt is non-negative, and this term here is related to the Lie algebra of the group. So it has this power t to 3 here, and then kg is the original sectional curvature. So the sectional curvature is always non-decreasing. So it's very good to make examples, to construct examples or prove new results concerning some positive curvature property. Okay, but then again, what is this relation with a Searle-Wilhelm theorem and hence to the space of positive scalar curvature? It happens that
Sorry,
okay,
Leonardo?
Yes, please.
Can I ask, what is Q? Maybe I got lost.
Yeah, sorry. I didn't mention it. Q is any bi-invariant metric on G. Thank you. Yeah.
Okay, thanks.
Yeah. Thanks for reminding me this. Yes. So yes, we have the product metric here on M times Z. We have this metric initial G, and then we take a bi-invariant metric Q here on G, introduce this 1/T parameter. Okay.
Okay, thanks.
Oh, no problem. And then you can see, I'm just give a quick explanation about this. When we denote by x bar and y bar, we are considering a vector that has both horizontal and vertical components, meaning that the vertical components are that are tangent to the orbits, and naturally the horizontal components are that are orthogonal to the orbits. And here and V are the elements of the Lie algebra that gives such action vectors when representing X and Y like this. And this P here, I'm going to explain in a bit, okay? But the point about Cheeger deformations is that they do not decrease sectional curvature. But then what happened is that it was conjectured that this result of Searle-Wilhelm could be demonstrated only using these deformations because it has a such intricate proof and it's very hard. And after a Cheeger deformation, they need to make some conformal change to take care of the analysis on some singular points. But it turned out that when Professor Llohann, myself, and also Renato, that is a PhD student of Llohann, and Professor Rafael Leão, um, we realized something, that if you have a manifold with an isometric action, a Riemannian manifold, and the D group has non-abelian G algebra, then the metric itself develops positive scalar curvature after a finite Cheeger deformation. And this is not surprising by one side, because Lawson and Yau had proved that when you have a manifold that admits non-abelian symmetry, then you can construct a metric of positive scalar curvature on this manifold. The problem, however, is that they need to break the symmetry of the group to prove the result. So they always reduce the group to the case of SO3 or SU2, and they take more careful estimates. Here we have things way different and easier, because we can just write the expression for the scalar curvature here in this manner. And I just can tell you that Vi and Vj's are vectors that belongs to the Lie algebra of the group. And this is the original scalar curvature. And this lambda y and lambda j are the eigenvalues of this tensor P here. Just because I already mentioned it twice, this P tensor is the tensor that maps the tangent space of the orbit to itself by making the correspondence between the metric G on the manifold with the metric of the Lie group Q. So if you can put G on two actions vectors, it is exactly to the metric Q deformed by this factor P in one of the entries of your metric, applied then to the vectors of the Lie algebra that generate such action vectors. Yeah, it's precisely this expression here. I will come back here in 1 minute. So this is the P that we have talking about a lot. So U and V are elements from the Lie algebra, and the U star and V star are the corresponding action fields. Okay, so when you take a look to this expression here, you can realize that the term that grows faster in the infinity is this one here. That happens to be positive whenever, if you take the asymptotic limit, you see that it goes with some t only, because we have to make some L'Hopital rule here. And this is precisely t, limit of infinity to t, times more or less the scalar curvature of the orbit when you see it as a normal homogeneous metric. But the problem is, if the group is non-abelian, necessarily there's some bracket that doesn't vanish. So we have we can ensure the positivity of a scalar curvature for long t. But what about fixed points? We can have some fixed points here, and this is where it all started the thing about Kasdan-Warner stuff, because we wanted to take a look to the tubular neighborhood of the fixed point set of this manifold and prescribe a positive scalar curvature function on this tubular neighborhood, and then make some glue in order to reprove Lawson and Yau theorem. But then we would not have this result about that G develops positive scalar curvature only by itself. But then how is this related with Searle-Wilhelm theorem? Because we never talked about the ZT term here. And the interesting thing is that when you have some fixed points, necessarily the ZT, it does blow up when you go to infinity, given the presence of fixed points. And this is a crucial thing that Searle and Wilhelm didn't know by the time when they where they were trying to understand how to live positive ridge curvature. Indeed, just a small correction. They were aware that such an expression would blow up in the presence of fixed points, but not in other cases that Professor Sperança and I managed to analyze it. But they never wrote this theorem here in any place. But we were the first that did it. But after this, they commented to us that they were aware about it. But then we have proved that the metric, any initial metric that we start that happens to be invariant by the G action, develops positive scalar curvature after Cheeger deformation. Well then, so there is the first insight to the conjecture. We can think, for instance, that the space of positive scalar curvature metrics that is invariant by the group action must be path connected, because, well, it should be true, because every metric that we start, it develops positive scalar curvature after some time. Okay, and before coming here, I just would like to mention how, what can we say about this conjecture, and how is it related to something that I'm looking right now, that are the modular spaces of matrices with some curvatures property. When we are dealing with this space of matrix, it's natural to make the following assumption. You start with a manifold, okay, that happens to have boundary, and then we start with a G-invariant metric on this manifold. Since the Lie group is non-abelian, we can always assume that this metric will develop a positive scalar curvature after some finite Cheeger deformation. So we have a manifold with boundary that is compact, and we take a G-invariant metric. Then after a finite Cheeger deformation, we obtain positive scalar curvature on this manifold. But then, to this modular space stuff, it would be good if you knew that this following conjecture is true. Suppose that you have a metric that has positive scalar curvature on the boundary of such a W, okay? And assume that your Lie group is non-abelian. Is it true that we can extend this metric G to the coboundary W to a metric that happens to be also G-invariant and has positive scalar curvature? Okay, so you see, we have the boundary and it has positive scalar curvature. Can we just extend this metric to the coboundary by preserving G-invariance and positivity of the scalar curvature? And well, at least we could think that this generalization of Lawson and Yau results could imply the conjecture, but it doesn't, because of the following. This Lawson and Yau result, it states that for big T, we have positive scalar curvature. So we can find some A here, such that our metric has positive scalar curvature. But we do not know anything about the behavior of the scalar curvature on a Cheeger deformation. Meanwhile, we do not get very close to the infinity. Okay, so this was a problem to achieve this conjecture. However, if the space of matrix of positive scalar curvature that is invariant happens to be path connected, then we can prove this conjecture. And this can be simply proved because, well, we make this very large Cheeger deformation. We start with any G-invariant metric on the coboundary, okay? We start with any offset metric on the coboundary. Then we make a Cheeger deformation in order to this metric has positive scalar curvature. Then naturally we take the immersion metric on the boundary of the manifold. And then since this space is path connected, the space of matrix of positive scalar curvature there on the boundary, then we can take this metric of positive scalar curvature that you want to prescribe, and they make a path between this metric and the isometric immersion metric. And then we glue everything and prove the conjecture, only assuming that this space of positive scalar curvature that are invariant is path connected. So this was also a motivation to approach the problem of, at first, at least showing that this space of positive scalar curvature is path connected. But then, since it's very hard, and I would say that is impossible indeed to understand the behavior of the standard Cheeger deformation, meanwhile we are not that close to the infinity, we need to go a little bit further and introduce a more general version of a Cheeger deformation. Instead of deforming the metric here by the parameter t, what if we multiply it by some positive G invariant function? Okay? So we multiply it here by a positive G invariant function. And then it also summarized by this expression here. We have that the P tensor is the one that makes the correspondence between action vectors computed on the original metric to the corresponding vectors that generated these action vectors on the bivariant metric. And then we preserve by Cheeger deformations the horizontal and vertical decomposition. So the metric is the same on horizontal directions, but on vertical directions, we gain this thing here, this deformation here of the metric on vertical directions, where h is an invariant function. But why I am writing this like this manner instead of making the standard procedure of Cheeger deformation? Because I want to make it clear that, well, we do not need to assume that h is positive, okay, to get something that is positive definite, and hence a Riemannian metric. We just need to be careful that this operator here, 1 plus h times p, is positive definite, okay? So we may allow h that are negative, and this is very important to us. And then a deformation induced in this manner is what we call an Cheeger deformation. And what is the idea? The idea is to look to analytical properties of this map here, the scalar curvature map of a generalized Cheeger deformation. So if you get a distribution here on this G invariant Sobolev space, W to P, and then we send it to the LP space of the scalar curvature of D applied to this H, meaning that the Cheeger deformation, Cheeger deformed metric G by its H, we're going to look to analytical properties of this map in order to prove our contractibility result. And how can we do this? Okay, also after coming here, I'm going to say a few words about why should I care about this map? Because we have the following. During this presentation, we shall assume that M has no fixed points because the analysis must be made a little bit differently under the presence of fixed points. But for the idea so far, we have the following. There is an open domain on W to PG that includes the zero, where the generalized Cheeger deformation is defined, because we are allowing H to be negative, okay? So when we restrict our operator, our scalar curvature operator here to this domain, it happens that on zero, we obtain the scalar curvature of the original metric. Moreover, this LG is an open map, meaning that if you want to prescribe some function as the scalar curvature of a Cheeger deformed, H Cheeger deformed metric, then we can always do this, because this LG-H map is an open map. So you give me a function that is G invariant, I can always realize it as the scalar curvature of a generalized Cheeger deformation, okay? So the corresponding PDE associated to the expression of the scalar curvature of a H Cheeger deformed metric is solvable. But we do need here, and this is the more difficult step, is that this map LG, it is injective, meaning that the solution is unique. If you want to prescribe a function as the scalar curvature for some metric that is realized, that is of the form of a generalized Cheeger deformation, then you can do it uniquely, meaning that you can find only one H that realizes such a prescription. And how with this can we prove the conjecture that the space of metrics is contractible indeed? We do this the following. Suppose that G is non-abelian, if fix some metric of positive scalar curvature that is G invariant, okay? And then take any G0 here that you want, and then make the convex sum of the matrix. It's not true that a convex sum has positive scalar curvature, as you may realize, otherwise the problem would be not relevant at all. But then let's do something that's a little bit different. Let's consider the convex sum of its respective scalar curvatures as well. Okay? Then we show the following. We shall prescribe this ST here, and we take as background metric this GT here. And then we show that when we want to prescribe this ST with background metric GT, for each T, there is only one HT, that the HT Cheeger deformation of GT has as a scalar curvature ST. Okay. And then, since ST is positive, we built this path of matrix of positive scalar curvature between G0 and G1. But then since HT is unique, and this is the very important thing, H0, H1, they are 0. And then this is a path indeed between G0 and G1. So the path is just given by this generalized Cheeger deformation of the convex sum metric. And this shows not only path connectedness, but also by taking a look that these functions here can vary in a continuous way, show the contractibility of the space. So it only remains to us to prove that our PDE has a solution if the solution is unique. So by very simple arguments, we could show the contractibility, and also once we have path connectedness, we could prove this more general conjecture about extending positive scalar curvature from the boundary to the co-boundary. But why we had to approach by a generalized Cheeger deformation, but not under like conformal chains and other different methods that are more or less classical in the scenario, like we have proved this G-invariant Cassel-Werner problem. Well, prescribing scalar curvature is underdeterminate in the sense that many metrics have the same scalar curvature. But then a very useful approach is this one of Kasdan and Warner that we also made this on our invariant scenario, that to the people that works with geometric analysis may know that this is a critical exponent here to the analysis. But when we are restricted to the G-invariant setting, and under some assumptions of the isometry group, then we can always solve this PDE, not needing to take a look to the Yamaba invariant and stuff like this. And then what can be shown is that if we take the conformal class of our initial metric and take this intersection with the positive scalar curvature metrics on the manifold, meaning we just consider conformal chains of the initial metric with positive scalar curvature, then it can be shown that this space is contractible. Therefore, the space of matrices of positive scalar curvature is weakly homotopy equivalent to the space of matrices with scalar curvature equals to 1 on the manifold. So, well, maybe we could prove that this space of matrices with scalar curvature equals to 1 is indeed homotopy to a point. But, well, this cannot be done because this space here, when we consider only matrix conformal chains of our initial metric that has positive scalar curvature equals to 1, this is non-compact for several examples. This is due to Brendel and also Brendel marks. But the G-invariant setting is better behaved. But also, we cannot solve the problem looking to this conformal change metric because we cannot guarantee uniqueness of the solution. So the reason why we take a look to a generalized Cheeger deformation instead of looking to the conformal change that show it to be successful when prescribing G-invariant functions is that there is no way to guarantee uniqueness. Indeed, the approach to this kind of problem is very rational, so you may expect a lot of solutions. But then when you have this Cheeger deformation stuff, you guarantee that you have uniqueness of solution. The open map part is quite easy. Indeed, we write the analogous equation to the scalar curvature of H Cheeger deformation. And if you make H to be constant equals to T, we recover the expression for the other slide. But the interesting thing here is that the leading term, the high order term here is just the Laplacian. And its principal symbol here is the principal symbol of the Laplacian, and then our PDE happens to be invertible. And since this expression is a scalar curvature expression, it consists on a quasi-linear PDE. Okay, and Kasdan-Warner happened to prove that for a general kind of scalar curvature map, meaning any map that has as its image as the scalar curvature of some metric, then this condition of the symbol of the operator being invertible is also sufficient to use an inverse theorem to show that this PDE has a solution. So this simply comes from the fact that the leading term here is the Laplacian, and then this is a quasi-linear elliptic PDE, so we can solve it locally. But the problem is indeed the injectiveness. And I'm just make it very quickly because I'm almost with no time, but I think that is quite interesting. Because we could realize that
Leonardo, to be
yes.
clear, you have 10 more minutes, okay? I think you're fine. I think you're good. I think you're good.
Okay, good. But I don't have that many slides as well. I just want to make some suspense, I guess, because people, let's see, because this is the hard and fun part, I guess.
Fair enough.
Party as well, I guess, because we always have some fun doing this. I mean, when we are not having fun. But then the operator, it enjoys the property that if we take the t, so we consider the original metric being t times g, where t is positive, then this expression for a generalized Cheeger deformation, it gets the following Hay scale here. And what a surprise was that this LTG here converts uniformly to a multiple of the identity in every bounded subset of the domain of our operator. Okay? This was very, very interesting because very close to when t goes to infinity, we approach the identity or some constant positive multiple of the identity. Okay? And this gives us some very good hints about what to do. At first, we tried to do some perturbation of the identity to prove the condition of injectiveness, but we were not able to do this, so we had to make something that was more classical. Well, we know that L prime G is invertible because of the linearization, and just mentioned about this Kasdan-Warner stuff, and the main term on the PDE being the Laplacian. Then we can construct a vector field defined on an open subset of this Banach space here. Okay, that is just a linear space. And then this is the vector that we consider. We just take here L prime times G applied to H, then its inverse, and then we just take the DT derivative of this map. And this is our vector field. And we can show that if you reparameterize it, the corresponding flow of this vector, okay, this is defined by a Lipschitz field. So by the classical Picard-Lindelof theorem, we can guarantee the existence of a flow. And it happens that this is a Lipschitz field. We can see it by showing that the curve phi-th, it has finite length. Phi-th does not escape from the domain, and also it enjoys this scaling property. Then you can show that this is a Lipschitz vector field. Okay, and then what is happened that we get convergence of this flow at the infinity as well. And what I will make you clear is that at the infinity, this flow phi applied to 8 is nothing more than our LJH, that is the expression for the scalar curvature of a generalized Cheeger deformation. But then, since flows enjoys the property of being homeomorphism, necessarily our LGH is an homeomorphism. And then we have proof injectiveness. So we just need to guarantee the convergence of the flow. But how can we do this? Well, we want to make global pictures of what can happen here. And since we introduced this parameter t, and then we take an interval I, and then we take times m, and we consider this map L here. We can prove that this map, it has as level sets submanifolds that have dimension 1. So these are curves indeed. So these are the curves. And it could happen a lot of things like this. This could be the possible lines on the inverse image. But then again, by the discussion that we made, we are choosing this vector field in a way that the flow lines here, when we look to this generalized vector field here, where the second component is just that vector field x, and the first is ddt, it parameterizes the sublevels manifolds of L minus 1. So this vector field we just introduced, they parameterize the level sets of the scalar curvature function.
Leonardo,
yes, please.
Are you going to talk about the blue and yellow cases?
Yeah.
Okay, good. Because I'm a little perplexed. I would expect these curves to have the boundary contained in the boundary of the cylinder. So how can they?
Yeah. So I'm going going directly
Okay.
there. Okay. So yes, let's talk a little bit about these curves here. Okay.
Okay, thanks. Yeah, because the other ones are fine, right? These are very weird.
Yeah, though this is the hardest one that we call it as no escaping thing. Okay.
Cool. Go ahead.
And,
yeah.
Yes, and the thing is that we can show that the inverse images, they all live in a fixed cylinder, and we do this by looking to Schauer estimates to the elliptic PD. But to look to the Schauer estimates, we need to guarantee that some no escape thing happens. For instance, when we approach the boundary of our domain that I just said, we need something that's positive definite. So we denote this minus 1 over lambda here to the function to be something that's not positive definite. Then, or if you take h, the C0 norm of h going to infinity, then this should be a plus. We show that the scalar curvature indeed blows up, okay? When we approach the boundary, both of the domain of our operator, or if we take h with a huge norm. Then it happens that this operator LGH, it blow ups. And once this blow ups, this is some contradiction with the fact that our PDE is elliptic, and we can use the Schauer estimates to guarantee that this cannot happen. Okay, so the point is that we never have something like these two curves here come to the boundary, because we have some a priori estimates given by Schauer just by looking to the PDE. We need to make the computations to show the boundness, but also is that when you look to the asymptotic behavior of both the h function being huge in C0 norm, but also to come into the boundary of the domain, we have this blow up that's not allowed by our Schauer estimates. So cool. This is why we need to live in a fixed cylinder. And then something like this cannot happen because we have a flow line, and it also must be we always must have one flow line gets to the end, because at the end we have the identity. Okay, the flow we have the identity because of this asymptotic lemma here. So this operator must converge to the identity. And then it turns out that we only remain with this case, but only one flow line can get to the end indeed, because we have this more or less like Lipschitz condition that shows us that only one flow line can get to the end. So the final picture is this, and then we obtain it LG in H as the phi at infinity. So LG8 happens to be an homeomorphism, and this guarantees that our solution that always exists by some classical elliptic theory happens to be unique. And this finishes my presentation. So thank you very much.
Great. It was very interesting. Thank you.
Thank you.
Have we got questions for Leonardo? There's a lot to unpack there. You can ask point-wise questions about little bits you'd like him to expand. It doesn't have to be a very profound question.
Hello, may I ask something? Hello, how are you?
Go ahead, Daniel.
Yeah, please.
Haven't
Please.
seen you. Nice to see you again. Which type of groups are you thinking of? I mean, there are groups of isometries, but like S1s or what?
Yes.
Collections or what?
Yes, you can think of any group that is non-abelian. Okay, so you need to S12, SU2, SO3, or something related to this. You have to it always holds for non-abelian algebra. Okay, and if when you have non-abelian algebra, this is also related to the fact that the orbits of the manifold of the G action on the manifold have finite fundamental group. This is more or less like a correspondence, I guess, by the works of John C. Nash, I guess, in the 60s. But yes, I only require that the group to be compact as well, yes, but with a non-abelian Lie algebra, just it. So you can think of, for instance, like S3. The symmetry
well, S3 and S1 are the typical cases before, right? Of this
yeah. Yeah, but we didn't have this contractibility stuff, right? We just had that these manifolds admitting non-abelian symmetry, they develop positive scalar curvature. There's no mention about the space of positive scalar curvatures being contractible. Indeed, this is not the case if you do not assume symmetries. Okay, and the point is that the presence of symmetries, it's non-abelian symmetry, that ensure the existence of a metric that is invariant by the symmetry of positive scalar curvature, is the crucial hint here that gives us that it may be possible that this space is contractible, and it happened to be. So yes, it's totally related to the non-abelianness of the group.
And my second question, another question is, it's a technical question. I mean, when you have this Sobolev stuff, I mean, do you use these results of that you reduce the dimension by the quotient of the manifold and stuff like that?
Yes, you mean like the Abbe and Vogel result, right?
Well, yeah, like... I mean, that result has been recycled many times. Yeah, I mean,
yes. Myself, I just recycled it very recently. So yes. We do use this, but not here. But we use it when you want to make the Kasdan-Warner problem of prescribing G-invariant functions as the scalar curvature of G-invariant metrics. So the only thing that we need to assume to use this result is that there exists at least one orbit of positive dimension. I know that it's classical that people assume that the orbits have a infinity cardinality, but no, we don't need it. We just need that an orbit to have positive dimension.
So you recycle the theorem, you reprove a new theorem to because I mean because the theorem says if you have no fixed points, basically you can do that.
We don't need the non-existence of fixed points. That's the crucial part, because we use some slice theorem to reduce the analysis to the regular part. So that has a nu zero measure.
So I mean, so this Yamabe type equation is, I mean, you have this implicit function theorem and openness. You are doing some type of how do you say, of continuity methods. Those are the tools, basically, right?
Or... Yes, you can think of it, but in this case here is simple. To the Yamabe case, we just use variational methods by dealing directly with the critical exponent. So because we have a better compacting beds and do this generalization of Contrakov. But here in this theorem, we just use inverse function theorem because Kasdan and Llohann, they have proved some existence method for elliptic PDEs that are quasi-linear here and are of this kind of scalar curvature. And this only uses Banach inverse theorem. So it's more or less say that, well, only the linear part plays some role here in the invertibility of the PDE, because the PDE is quite quasi-linear. This appears in some paper of Kasdan-Warner on the subject. Yeah, we do not need to use it.
You do use a priori estimates to prevent blow-up, but it's not as part of a continuity argument, right?
No, not at all. Not at all.
That's right.
No.
Both tools intervene, but so maybe one could rewrite all this by using some sort of continuity method.
No, that's what I mean.
The implicit function theorem in one context and the a priori estimates in a slightly different sort of problem solving, you know, just avoiding all the difficult cases, so preventing
I totally understand it. Yeah, this is something that we definitely are taking in consideration, because we never made this paper public yet, because it's quite recent. But yes, this is good. Yes, you realize, yes. Yeah, I appreciate it. Yeah.
Yeah, congratulations. I mean, it's a nice mixture of analysis with geometry. It's a nice work. Congratulations. I enjoyed your presentation.
Oh,
I mean, I'm happy to see you somewhere. I mean, but I mean, it's a good presentation. Thank you.
Thank you. Thank you very much.
Yeah, good stuff. Can we talk about dimensions? I tend to like specific dimensions. So for instance, just let's start with a curiosity. In the result by these two guys, and you displayed at the beginning, what's the problem with 8? Being at least 5, I can live with this. This is fine. But why not 8? What happens at 8? Ebert, yeah, that's right. What's going on there?
You know that. Let me. You know that I really don't know, but I think that it has all to do with the existence of only one exotic structure on S8. Okay, because we only have one 8-dimensional exotic sphere, and I think that this should play some role here, but I'm not sure why. Yeah, I really don't know. Yeah. I know. I'm sorry. I'm very sorry, but of course, I just wanted you to take a look to this paper and see how ours is very easier to deal with. You know, just kidding. Yeah, I really don't know it. Yeah.
Okay.
I should know it, but I don't know.
It would be interesting to know what's happening. You know, that's too specific. So
yeah.
I will be interested to know. But then let's go to the real questions. So Daniel asked you about some sort of examples. Which examples can we have in mind? So maybe S3 would be a sort of. But does the dimension of the isometry group, does the dimension of G face any constraints, or if G has any? You know, we've heard about dimensions of M, right? But what about the dimension of G?
No, we don't need any constraint about the dimension of G.
It doesn't matter at all.
No, at all. No. Not at all. And so, for instance, if you want something that's quite nice, is that all exotic spheres that admit positive scalar curvature, they enjoy the property of the corresponding space. So if you put some exotic sphere here, it also happens that is homotopically equivalent to the star, because to a point, because they are almost always admit actions by non-abelian Lie groups. The only case where they do not admit are the 10-dimensional case, and they are not the boundary of any spin manifold. So yeah, there are huge of applications on exotic spaces here, and also Lawson and Yau result was in this direction as well.
Yeah, is Andres in the room? Andres Moreno, are you there? If you're here, give us a sign.
Yes.
Okay, good. Andres, so can you think about our examples of metrics on S7? Because then, right, we have looked at these isometric classes of G2 structures, and then if you move from a class to the other, these are, of course, in this case, I think they are S3 invariant, right? We produce S3 invariant metrics.
Yes, and in fact, it was a question in the Juliet's defense about the property of the curvature for that metrics that we work. I don't know. I never.
I think it might be worth. I think it might be worth having a look at those. So just Leonardo, just so that you don't float around. So this is. So we looked from a different perspective, right? From perspective of G2 geometry, but nonetheless we're looking at S3 invariant metrics on S7. Right? So in this case, it would be interesting to see whether, you know, we could pose similar problems. So which functions can be realized as scalar curvatures of said metrics in this context. right?
I see. But the matrix must be related to G2, right? You must preserve the G2 property, I guess.
Yeah, but now,
Yeah.
precisely. My point is, you have a result that says, look, in favorable conditions, these are the metrics that realize, these are the invariant metrics that realize your scalar curvature. And on the other hand, I'm saying, these are the metrics you obtain from a G2 structure. Now, how about how many of these corresponds to an actual G2 structure? Is it all of them? If it's all of them, that's a theorem.
Yeah. That's interesting. Yeah, because every function can be prescribed. Every ST invariant function can be prescribed as the scalar curvature on a metric on S7. But definitely, it cannot be the case that all of these functions are related to a metric that happens to be G2, right? It cannot be the case. Yeah. But very nice.
It would be great to think about this. There's a paper Andres wrote with me. So I suppose I did something on it. So that we released this year a preprint just about G2 metrics on invariant G2 metrics on S7.
Yeah, I saw it.
Good. So if you happen to stumble into this again, then it would be nice to hear your take on this. So how many of those G2 metrics would fit into your narrative? So
it would be nice. Yeah, it would be nice to impose some new constraint, and perhaps this uniqueness thing of generalized Cheeger deformation. Perhaps you could take a look, for instance, of what happens with a G2 metric and when you make a generalized Cheeger deformation of it. Is there any parameter where it still to be G2?
Cool. What happens and what happens to the torsion?
Yes, exactly.
Because we want to produce G2 structures with as little torsion as possible.
Exactly. Now you reduce a very difficult PDE to a PDE only in terms of a function, right? So yeah, that is H, the parameter of the Cheeger deformation. Yeah.
Good stuff. Very fair point. I'll probably engage you guys. Let's wait for Andres' scholarship to kick in, and then we'll probably engage with you guys to discuss this point in private. But thank you. That's very thought-provoking.
Yeah, thank you. Thank you.
Good stuff. Any more questions for Leonardo?
May I, if there are no questions, may I? So you're hanging around in the positive curvature case, right? Because basically you're dealing with isometries. Do you think that you can do something with a less restricted group than isometries in the negative case?
No, negative case for real. No, there's no way of doing anything of like this, because all the tools that I know that are related to Cheeger deformation stuff, they are only for positive stuff. So there's no way, because Cheeger deformations, they always do not decrease curvature. So
I mean, one thing is the group that is acting, right? That if you know that you are in negative, there is a big problem there, right? But so you said that the big problem comes from Cheeger deformations. Right?
Yeah.
Okay.
Yeah. Exactly.
I'm not familiar with Cheeger deformation. Thank you.
Yeah, they will just ruin everything in terms of scalar curvature, because they are tempted to make it positive or at least zero at some point.
I see. Cheers. Thank you.
So is this on the archive just yet?
Not yet, but hopefully next week, because I must prepare to the Unicamp professorship position, right?
Yeah. Careful what you wish for.
Yeah, looking forward to it. Yeah. So yes, but next week definitely. Yes, Llohann and myself are just finishing it.
Okay. Chill. I'll be very interested. Drop me a line if you.
Yeah, for sure.
Okay,
cool. For sure.
Thank you. All right, let's wrap up. It's 10 minutes past the hour. Paolo, do you have any questions?
No, thank you. No, I was enjoyed very much your talk. I apologize for arriving late. Very happy to see progress, very impressive progress in your research.
Thank you, Paulo. Thank you. It's always a pleasure.